So I'm going to look at what's called solids of revolution. So we're looking at rotating a function around the x-axis. So it's quite a challenging idea, and it'll draw on a lot of things we've learned already about integration. So let's jump into it. This is what it says. It says if you're rotating something around the x-axis, then the volume of that object will be equal to pi multiplied by the integral from a to b of f of x squared dx. And what I want to do in this video is sort of unpack where exactly that comes from with an example. So, let's start hopefully nice and simply, and we'll look at this red line here. This is the function f of x equals x. So just a linear line. And we just said, we're just going to say that the domain is from A to B. So A here is pretty much at the origin, and B here is just at some other point to the right of A, right? Okay, what we want to do from here is we want to basically rotate that around the x-axis. Now, here is my beautiful attempt to do that in 2 dimensions. It would look something like this, right? If you took that line f of x equals x and rotated around the x-axis, I hope you would agree that you get something that looks like a cone. And if you're not convinced, here's one I prepared earlier. We can do it in 3 dimensions. So what we have here is just a Cartesian plane, but you can sort of see it. This blue line here is what's called the z-axis now. So now we're in 3 dimensions. And what we've got here is, the line y equals x. And what we're going to start to do is move it into that 3rd dimension by rotating it. So it's going to look something like this. If I can get it to play. Okay, so there's a bit going on here. But you can see if I sort of change the perspective now, what that line is doing is it's rotating around the x-axis. So we get what's called a solid of revolution. And you can see here, pretty nifty, huh? Gives you a cone-like shape. And our question is, what is the volume of that shape, right? So that's our job. So let's go back and see if we can do that. So what we're going to say here is we're going to have to deal with our 2D representation. The best drawing I can do in 2 dimensions. Okay, let's take some point on this function, f of x, and let's call that f of x. So this point here is at f of x, so it's some point. It must have a height of f of x, right? It's the function evaluated at x. Okay, then we're going to take some point to the right of that, which we're going to call x plus dx, some small distance dx. So that's going to be x plus dx, and then I hope you would agree that the height at that point would be f of x plus dx. Okay, so what we get is, these 2 points, and then what we're going to do is we're going to connect them, and we're going to make a shape here. And remember, we're in 3 dimensions here, so I encourage you to think about what shape this is, right? I hope you would agree that it's a cylinder, okay? If you sort of take a vertical slice of your cone, you would get a cylinder, right? Or something very close to a cylinder. And when I say close to a cylinder, you're probably like, this doesn't look like a cylinder. But if we took those slices to be really, really small, the distance between f of x and f of x plus dx would get really small. So essentially we have a cylinder, okay? And so, we get this sort of cylindrical cross section. And then what we want to do is we're just going to say, okay, well, let's think about it this way. The height of this cylinder is dx, yeah? Because if this points at x and this points at x plus dx, then the height must be dx, okay? And I think I've used the word height interchangeably. We're going to think from now on height being being the width or being this distance, yeah? Okay, and then this thing here, if we think about it in terms of a cylinder, would be our radius of our cylinder, right? This length from here to here, from the x-axis up to here, would be the height of our cylinder, which would be f of x, right? I should put that there. If we think about it from this point here, from here to here, then the radius will be f of x, right? Okay, and again, remember we're making these small, making this small, small, small. So as that gets smaller and smaller, the radius is equal to the function evaluated at x, yeah? Okay, so what we're going to do now is we're going to recall a few things. Hopefully you can recall from previous maths that you've done that the volume of a cylinder is equal to pi r squared times h. It's the cross-sectional area, which is a circle. cross-sectional area of a cylinder is a circle, and then you multiply by the height, which is h, yeah? Okay, then what you're going to do is you're going to just think about this example cylinder, right? So if we think about this example cylinder we've got going on here, well, to find the volume of that, it would be pi multiplied by the radius squared. Remember, the radius is f of x. So we're going to take f of x and we're going to square it, and I'm going to multiply by dx, which is the height of the cylinder. So we get this situation. Okay, and hopefully you're starting to see how it comes together. We can say now, generally speaking, that if we were to take these cylinders to be smaller and smaller, dx getting smaller and smaller, we would sum across all of them. So we take a cylinder here, take all these cylinders and add them up. And then hopefully you would agree the volume of all those cylinders added together would be the volume of this solid of revolution, this cone, right? And I'll put a link below to explain why the integral from A to B represents the sum of rectangles, or in this case, cylinders, because that is what the integral from A to B represents. You're taking the sum of those things. Anyway, so you get integral from A to B of pi multiplied by f of x squared multiplied by dx. And hopefully, you know, one of the properties of integrals is you can take any constants out the front. So we get what we have here. The volume of a solid of revolution rotated around the x-axis is equal to pi multiplied by the integral from A to B of f of x squared multiplied by dx. And hopefully you can sort of see geometrically why that's the case. All right, good luck with all your work.